Yes, number one. Yes, we did not finish that that document. We still have a lot, and we cannot finish it. Oh, I ran out of copies again. So, but I can borrow one. I don't think I posted it here. Did I? The limit document. Can I borrow it for a minute? Okay, what am I doing?
Number 6.
Number 6. Really? Okay, let's do number 6. I thought that that one was good enough. So 1 plus h minus 1. So we have limit. The square root of 1 plus h minus 1 divided by h as h approaches 0. So as I mentioned several times, please remember you cannot erase the limit operator. You cannot drop the limit operator till the last step. Okay? So first of all, what do? I'm asked to determine this limit. What is the first step?
Again.
Right. So the top is
-1. 0.
good. The bottom is
0.
good. So it's a limit that is 0 over 0, which is an indeterminate, the first indeterminate case that we looked at. And there is hope, right? Good. So what type of limit this is? Is it a factoring? Is it a simplifying? Is it rationalizing? Is it what?
Rationalizing.
Good. So then, because we have all those, and we are going to add more to that list. You all have this document, right? The limit document, right? You all have it? Okay. So what do I multiply and divide by?
Square root of 1 minus h plus 1.
So do I have to continue? Is this good enough? Do I have to finish it? If you say yes, I'll finish it.
Yeah.
Okay. So this is limit as h approaches 0. 1 plus h minus 1 over h, the square root of 1 plus h plus 1. These two go away. Eventually, h will go away. So this is 1 over 2. This is the final step. This is when I replace h by 0. The top is 1, the bottom is 2, and this is why the limit operator disappeared. It cannot disappear before that final step. Okay, anything else? Is there anything else from anything that if you have questions?
Yeah,
Yes.
so on page 107, number 38, it was if 2x is less than or equal to function g of x, which is less than or equal to x to the 4th minus x squared plus 2. For all x, evaluate the limit of x as limit of g of x as x approaches 1.
Good. So we had a similar problem last time. I just want to show you where it is. Well, for some reason I probably closed it. Okay. And once I show you this, if you still say, yes, I want to take a look at it, here it is. So we have this situation. So this was the Squeeze Theorem, where we basically were given the first step, which is the first hypothesis number 1, which tells us that the function was squeezed between two other functions. And we determined the limit of the left function, the lower function, and we determined the limit from the right function, or the upper function. And then we concluded that from number 1 and number 2, the limit must be such and such by Squeeze Theorem. Is that good enough? Yes? Is that good enough for this one? Okay, anything else? Do we have anything else? Is there anything else you'd like to ask? If not, I would like to start. Yes? Anything? Anything else from the limit document?
Number 10.
Number 10? Can I see it?
Yes.
And number 10. Yes. So you're applying the limit from f of x times the limit of g of x. And you determine the limit of f and you determine the limit of g. So this was the limit of f times g as x approaches, what was it, 1?
2.
2. So this is the limit of f as x approaches 2 times the limit of g as x approaches 2. You determine the first one, you determine the second one, and multiply them.
Okay.
Anything else? Can I just see it, because I think there are a couple of things that I did not show here. Yes, I want to show number 7, number 8. Did you have any difficulties with number 12?
You told us to hold off.
Yeah, you said to do that.
Okay, very good. So 12 we have to do. So 7, 8, 9, 12. Did you have any questions about number 2?
Didn't tell us.
Okay, so let me just write this down here. Number 1. So for number 2, I showed an example last time. Do you think you can work on number 2 for Wednesday? I showed an example with the absolute value last time. So number 2 for Wednesday. Yes?
Yeah.
Okay, and number 3, we did that. Number 4, just the first one, what would you write? Limit of sine x over x as x approaches 0 is. So let's, okay, yes, so please write that 1, and we have to commit this to memory. Then the next one was the limit. So I want to show you number 5, although we did not work on number 5 together, correct?
Correct.
Okay, so limit is the square root of 16 minus x squared, right? As x approaches 4 from the left. Is that, did I copy it correctly?
Yes.
Okay, so first, what I would like to do here is, and it's mandatory, we have to find the domain. We have to find the domain of this function. So forget about the limit for a moment. Please tell me what I have to write in order to find the domain of this function. I have to write something in order to find the domain. What would you? I cannot get rid of the square root. But I have to write something that I have to solve to get the domain. So the function is f of x equals the square root of 16 minus x squared. In order to find the domain of this function, I have to write what?
Sure.
In a moment, yes. Yes, but I have to write first what I'm doing. And why am I creating the chart? Yes, I will create a chart in a minute. So what do I have to write? 16 minus x squared, correct? Indeed. Without writing this, I will not be able to find the domain. It's the square root has to be taken or can be taken only from 0 or positive numbers. Good. So what type of inequality is this? Quadratic. What do I have to do? First, one thing I don't want to hear, move 16 to the other side and take square roots. It's not allowed in an inequality. It's allowed in an equation. First, I will multiply both sides by -1 because the leading coefficient is not positive. So I have x squared minus 16, and then?
Less than.
Very good. And now I will factor, indeed. So tell me how to factor x squared minus 16, and the factored form is?
X plus 4x.
Good. And now I will use the chart. The chart will help us. You don't have to. There are other methods as well. But the chart will help us to study the sign of this expression of x squared minus 16. The chart will help us study the sign of x squared minus 16. X is the variable in the problem. X plus 4 is the first factor in the problem. X minus 4 is the next factor in the problem. And then we have x plus 4 times x minus 4, which is what we are interested in. So the variable in the problem can be anything. But I'm specifically interested in two x values. And those x values are and
4 and -4.
exactly. I'm only interested in -4 and 4, and they have to be in ascending order. In the first row, I will have to write 0 under which number?
-4.
Perfect. Good. And what will I write for the product? Under -4, what do I write?
0.
Of course. When one factor is 0, the product is 0. What do I write under 4?
0.
Perfect. When one of the factors is 0, the product must be 0. So now it's very easy to understand this because you know that x plus 4 and x minus 4 are linear functions with a positive slope. So they come from which values? And they go to which values? So then all you have to do is just write the sequence of signs. Negative before 0 and positive afterwards. And now, on the first subinterval, I multiply two negatives. Both are negative on the first subinterval. What will be the sign of the outcome? Perfect. In the middle subinterval, one is positive, one is negative. What will be the sign of the outcome?
Negative.
And last one. So only now I'm asking myself, what do I want? What do I pick? Which sign do I want for the product?
Less than 0.
Exactly. Exactly. Well, that is the same with this, because I multiply both sides by -1. So I'm looking at the very last one. So then which territory will I pick? Well, I will pick
Everything beyond -4, or everything before -4, and everything after +4.
so which sign is less than or equal to 0? Negative. Where is this product negative? Perfect. That's the domain. So the domain of this function is -4 to 4, where the product is negative, not when the product is positive. Finally, now I can come back to the limit. Why do I need to do this? Is because if I ask you what is the limit of this function as x approaches 4 from the right, what would you say? So the limit of this function as x approaches 4 from the right, what would you say? Say it again.
No, 0.
Positive thing.
Look at the domain. Of course, it does not exist. 4 from the right. The function doesn't exist. How can it have a limit? Right? That's why we determine the domain. So if I say 4 from the right, you should say the function doesn't exist. How can it have a limit? So now if I say 4 from the left, what will you say? No. 4 from the left.
0.
0. What will you say about -4 from the right?
0.
What will you say about -4 from the left?
Does not exist.
That's the scope of finding, or the purpose of finding the domain. So this is very important. Okay, one more time. So then what do I say 4 from the left is?
0.
What about, this is from the left.
Oh.
4 from the left is 0, and 4 from the right is?
Does not exist.
Right, because the function is not there. Very good. So the answer is indeed 0. But this analysis, I will ask you to find the domain of the function. If something like this pops up, I will ask you to find the domain of the function first, because you may have other questions in there. I may ask you like I just did, -4 from the right, and you said correctly 0. -4 from the left, and you have to say D and E. Because how can a function have a limit if it doesn't exist on the territory? Remember I said a function can have a limit, right? A function can have a limit even if it's not defined at that point, but not if it's not defined at all. Good. So that was problem 5. What else we had there? If I could borrow the document one more time. So that was 5. That was 6 we did together. Yes, I would like to discuss 7, 8, and 9. Okay, here's 7. Do you remember that I said, please commit to memory a couple of graphs, a couple of functions? Do you remember which functions I asked? Tangent and arctangent. Very good. Perfect. And I'm going to list another few functions here. Here is one. Here is another. And here is the other. Okay, all these three graphs have to be committed to memory. Please, for me.
What's the last?
ln,
Natural log.
natural log x. I was going to get to it in a minute. So the first one is what type of function? Awesome. And it's the simplest possible rational function, and here is its graph. So the graph of the simplest possible rational function has to be committed to memory. Okay? So this is f of x equals 1 over x. The next one is an exponential function, specifically natural exponential function, and the graph is this. It has to be committed to memory. It tells us a lot of things. So for example, for the first one, if I ask you what is the limit of this function as x approaches 0 from the right? Perfect. The 0 from the left.
Negative.
And from the other side.
Both sides.
Either side of 0.
Doesn't exist.
So please put the answer in there on the document. Either side of 0. So the right-hand side is infinite, the left-hand side is negative infinity. From either side of 0 is the end.
Either side. Oh.
Yes, either side of 0. Now here, this will come into play in the next section after 2.4 and 2.5. So these are the limits at infinity. But now we can already say, as x approaches infinity, what do the function values do? What is the limit as x approaches infinity of e to the x? Infinity, right? Very clear. As x approaches 0, as x approaches negative infinity, what do the function values approach?
0.
And the last one is the inverse function of this. But again, does not appear till 2.6. But I wanted us to refresh our memory and remember these all the time, because they come up frequently. So now if I ask you what is the limit of natural log as x approaches 0 from the right?
Negative.
Perfect. 0 from the left. Right, the function is not there. Right. And what about the limit as x approaches infinity? Correct. Correct. Okay, the next one is number 8. And here's the notation for this function. It's called the greatest integer function. Greatest integer function. I like to call it a step function. It is a piecewise defined function. And here's its definition. Look at the 3 dots and 3 dots, which means it goes on forever. It's 0 for x between 0 and 1. Equals at 0, but not 1. It's -1 for -1 for x between -1 and 0. It's -2 for -2 and -1. It's 1 for 1, 2, and it goes on forever. Oops. Okay, here's the graph of the step function. Full point, open. Full point, open. Full point, open. full point, open, full point, open. 3 dots, 3 dots. Greatest integer function. So one more time, it says it's 0 for x between 0 and 1, but not 1, is 1 for x between 1 and 2, but not 2, is 2 for x between 2 and 3, but not 3, and so on and so forth. And now we can answer the question. What was the question? The limit of the greatest integer function was when x approaches 2 from either side. I have to determine 2 from the left. So limit of the greatest integer function x2 from the left, and limit of the greatest integer function for x2 from the right. What will you say? 2 from the left. 2 from the left is 2 from the left is 1, and 2 from the right is 2 from the right
2.
is 2, right? 2 from the right is 2, 2 from the left is 1. So what do you conclude for the limit, which is very clear on the graph? As x approaches 2 from either side, right? They're not the same. So s approaches 2, the left is 1, the right is 2, so the limit does not exist. Can anyone give us an example of a step function? Okay, I will give an example. I'm making numbers up now because I used to do my taxes on my own, but not anymore. It's been some time, some years. I don't know how the codes changed this year. I have no knowledge. So, but in the past, I'm making numbers up. For an income between 0 and 50,000, 20%. For an income between 50 and 80,000, 24%. For between 30%, between 50%. And that's a step function. Okay? Again, I don't know how it is done now. I don't know what changes were made, but that's an example of a step function. Another one in the past, before we all got to unlimited phone plans, for 0 to 1,000 minutes, 25 bucks. Making numbers up. Between 1,000 and 2,000, 30 bucks. Between 2,000 and 5,000, 40 bucks. That's a step function. It's a similar example. Now, let me look at the next one. Was 1 over t. What was it? Number 9?
Yeah, 1 over t, 1 plus t squared. Or the square root of 1 plus t, sorry. You're going to have to look at it.
Oh, okay. So I have to start from scratch. Sorry. So it was limit, I copied something else. So limit t approaches 0, 1 over t, the square root of 1 plus t minus 1 over t. Very good. So this is a limit. I would like to use a limit law and say limit of the first minus limit of the second. Yes? Approved or not? Not approved. Why not approved?
You can't just plug it in.
Right, because this is undefined and this is undefined. So I cannot even, in this particular case, I cannot even plug it in. So I have to do something else. And hopefully I will be able to plug it in. No cell phones, please. Okay, so what do you suggest we should do? What is the only thing that I could do here?
Multiply the other side.
There is no other side. This is not an equation. I cannot multiply. I cannot square. Say it again. Of course. Of course. I can only apply legitimate operations. This is not an equation. I cannot simply say square, let's square, or take the square root, or let's multiply or divide. Unless you are going to say rationalize the denominator. But that's not the case here, or not yet. That I would have accepted if you had said, well, but forgive me if I didn't let you. So if you wanted to say, well, let's rationalize, yes, but not yet. Okay, what is the least common denominator here? Very good. So what do I need to do? Very good. So I have 1 minus the square root of 1 minus 1 plus t. Very good. Awesome. Now I have to plug it in. This is my second attempt. The first attempt didn't work. I was not able to plug it in. But this is my second attempt. So let's plug it in. The top is, what do you hope for before you even say anything? 0. Yeah, you hope for 0 over 0, right? Okay. Yes. Do you all agree with 0 over 0?
Yes.
Okay. Now, obviously, you're right. So I do have to multiply and divide by something. But I have to analyze this and make a decision and conclude which portion of this function needs addressing. Because not both need addressing. So for example, the square root of 1 plus t is not a problem. Because when t approaches 0, that quantity is 1. So this is not the issue at all. But what is the issue? The t on the outside. 1. I cannot do anything to this poor t. I wish I could. There's nothing. Here I shouldn't do anything because it's not a problem. And to this poor t I cannot do anything. So the only problem is the top. The only problem that I can address is the top. How do I address the top? And we had an example 20 minutes ago. Exactly. So I have to multiply. I shouldn't do this here. Multiply by 1 plus the square of 1 plus t and 1 plus the square of 1 plus t. So the little t in the bottom is not a problem, although I would love to eliminate it somehow, but I can't at this point. The square root of 1 plus t does not create any issue because it's 1 when t approaches 0. The only one that I can work with is the top. But what do I get at the top when I multiply those two?
T.
So can anyone dictate?
1
Yes?
minus
Yes?
parentheses.
Yes. Awesome. Awesome. So once you say parentheses, that's perfect. Or you can also distribute from the beginning. But I find it's better to see parentheses first. Good. Because if we don't put parentheses, we will not distribute -1, and that will be a big issue. So then, limit as t approaches 0. I hope it's clear now. 1 minus 1 minus t becomes -t. And t, the square root of 1 plus t, and 1 plus the square root of 1 plus t. Finally, I eliminate simplifying and writing 1. So t divided by t is 1, t divided by t is 1. Now, and at this stage, I can drop the limit operator. Only now. It was our best friend till this point, and now we can drop it. So, when t approaches 0, what is the top?
1.
Careful. When t approaches 0, what is the top?
-1.
Perfect. And the bottom is?
2.
Yes, because 1 plus 1 is 2, and this is 1. So this is in D2, and you can write -1/2. Bless you. Very good. Is there anything else in this document that we need to look at? So, yes, number 12. For number 12, we have limit as x approaches 2 from the left and limit as x approaches 2 from the right. Can anyone give us the function from 2 from the left?
4 minus x squared.
Can anyone give us the function from 2 from the right?
X minus 1.
Can anyone give us the limit for the first one?
0.
Can anyone give us the limit for the second one? Can anyone tell us the limit from f of x as x approaches 2 from either side? Good. Anything else on this document? Is that clear? Everything? Oh, you don't have the document? You You do? Okay, if you do, it's okay. Everyone, you all have this document?
Yes.
Okay. I'll just hold for a second. So this is not done, not yet, not yet, not yet. Okay, that's all we have for so far. Okay, any questions for me? We're going to continue working on this document. It's not complete. We will still have sections in which we learn more, and we'll go back to this document. So now I would like to talk about 2.4, which is the precise definition of the limit. Hopefully tonight we will go into complete this and then complete the 2.5, which is continuity. And then hopefully the other 3 sections on Wednesday. Okay. So let me give you 2 scenarios. Here is one scenario. Here's a function. I'm making numbers up, of course. So let's say I have this. This is f of x. Let's say this is 2. And let's say this is 5. And I am going to write that the limit as x approaches 2 from either side of f of x is 5. According to my graph, will you agree or disagree?
Agree.
Okay, perfect. Okay. Now assume that I zoom in this area. I can put in the graphing calculator and just zoom in, and this, what I see is still 2 and 5. And let's say I continue zooming in, and I will still see 2 and 5. And I continue zooming in, and I can continue forever. But I will still see 2 and 5, correct? Would you agree? Okay. So what am I trying to say to you is this. That if I choose, I'm going to enlarge this because now I need to explain, and I really need it as large as I can make it so I can explain what I'm doing. So this is my f of x. This is my 2, and let's say this is my 5. So the fact that I can zoom in as many times as I want, as close as I want to that point, it shows that the limit exists no matter what I do, right? No matter how close I am to that point, the limit exists. When x approaches 2 from either side, the function values approach 5, correct? So I'm saying to you now this. Let's assume I choose a symmetric interval around 5. Very tiny. But I'm going to make it big so that I can talk about it. So let's say this is a symmetric interval around 5. So normally this length of the interval, well, it's double the length, right? But this side is denoted by 5 plus epsilon. Epsilon is a small number. What will this point be? So the length of the interval is obviously twice epsilon. Right, right. So I'm going to say this many times because I would like you to understand the mechanism, and then we will write the definition. So I'm saying this, that I can choose this epsilon to be 0.5. But then when I zoom in, it's going to be 0.2. And if I zoom in further, it's going to be 0.1. And if I zoom in further, I can make it as small as I want, correct? The limit still exists. I will still have the 5 right in the middle of the interval. If epsilon is 0.5 or 0.4 or 0.1 or 0.01 or 0.0001, it doesn't matter, right? I can always show this interval around 5, correct? Because the interval around 5 always exists, of course, for an epsilon positive. There is no discussion. Epsilon has to be positive. For any epsilon I pick, 0.5, 0.3, 0.1, 0.001, I will find a corresponding delta. Yes, you're right, but it's called delta. Oh, awesome. So I have this possibility. I have this possibility, and this will be 2 minus delta, and this will be 2 plus delta. Or I have this possibility. This is the second option. There is only one option, but I have to show you both, and we'll discuss which one is the one that we have to pick. I'm starting from scratch. For every epsilon that I pick, and I create the open interval, symmetric interval around 5, I will be able to find a corresponding delta around 2, and we'll discuss which one, such that every time I pick x close to 2, smaller, the distance is smaller than delta. One more time. Every time I pick x close to 2 with the distance between x and 2 smaller than delta, where will f of this x fall? Close to 5, smaller than epsilon. So it will be close to 5, smaller than distance called epsilon. But now the problem is, which of these two intervals will I choose? Will I choose this delta, or will I choose this delta? Before you answer, here is the mechanism if I choose the wide delta. What if I pick x here? And then it's outside. So that's not a good one. Which of these two will I pick then? Always the smaller one. So this is what I have to pick. So that is my 2 plus delta, and this is my 2 minus delta.
Could you say that again, please?
Why do I pick that one?
But, yeah, I'm writing it.
So for every
One's right there.
epsilon, I will find the corresponding delta. But depending on the graph, I may have this one as delta, or I may have this one as delta. The reason why I have to pick the smallest one at all times is because if I pick x here, look what happens.
It's on the outside.
It's further away than epsilon. So I have to pick the smaller of the two, such that every time I pick x, within delta from 2, f of x will
Always has to be within epsilon.
always be within epsilon from delta, from 5, from the limit. Why does this happen? Because the limit exists. Let me give you the counterexample, because that will probably help a lot. Here's the counterexample. And there is a keyword here that I did not, I did use it, but I did not ask you to pay attention to it. I'm going to use it again, of course. So here is the trick. So let's suppose I have this function. Right? So now assuming that I'm looking at this function, I zoom out, and I'm so far away, that this kind of, they melt, right? They kind of, I see something like this, and I will tell you, as x approaches 2 from either side, you will say the limit is 5. But now I zoom in, and I say, okay, and you can say, well, the limit exists. Because if I use this epsilon, look, you can find your delta, right? So the limit exists. But the key word is for any epsilon. For any epsilon, the limit does not exist. Look at for this epsilon. I cannot find the interval around 2. There is no interval around 2. This is possible. No matter how small I pick epsilon, I will always be able to find a delta. No matter how big is epsilon or how small epsilon is, because the limit exists. But here, you can say, well, I can show that the limit exists for this particular epsilon. Yeah, but it doesn't exist for this epsilon. And the key word is for any epsilon. I will be able to find the delta around 2 such that the limit exists, such that
So
every time
how would you say that it's possible then? Or you can find it for epsilon plus whatever? Or
the limit
minus
doesn't exist.
no matter what.
No, because I have to show for any epsilon.
All the time, every time.
For any epsilon. So don't forget what you want to ask. So we are going to start with a numerical example so you see how this works. So for example, if you say epsilon is 0.1, I will make my calculations and give you delta 0.01. Then you say epsilon is 0.001. I will make my calculations and I'll give you the corresponding delta for the epsilon that you picked. And I can continue forever for any epsilon you want, but not in this case.
Because there's no limit.
Because the limit doesn't exist. And we will not be able to repeat the process. You giving me epsilon and I giving you delta back for any epsilon. Because the limit does not exist. Yes, please.
So does this only work for continuous functions then?
It was for any function that has a limit. Continuous functions don't have to have,
But the one, the limit
Very-
coming from the other.
it doesn't matter, correct. So if you remember, the function is not defined at this point, but the limit exists. So that function is not continuous. I made the example continuous, but it doesn't have to be. There is an open point here. It doesn't matter. So the function doesn't have to be continuous for the limit to exist, as long as both sides go to the same number. Continuity is a different story, and this is the next section in this chapter. Yes, please.
So if this function right here has arrows in the end, it would work. But say the function was solid points, would it still work?
You're talking about this?
Yeah, so if as
And
opposed to the, if the line continues, it works, but if the line stops, would it still work?
It doesn't matter because we're talking about the limit around this point, and we want to show.
As long as it stops with outside of epsilon and delta, it would work. If it stops within, then it wouldn't be able to work.
The question is not to make epsilon big. It's to show that for any tiny, as small, I can make it as small as possible, the limit exists. Not to go the other way.
And would a question naturally
So
say?
if the function only exists between 1 and 3, I don't care what happens outside. We're talking about the limit around 2.
So on the other chart, if we go back to the other chart, let's say it was 2 and 1, it would exist then, right? If the epsilon was 1 instead of 5.
As long as I can show you that for any epsilon you pick, I give you a delta. If there is one epsilon for which you give me a value of epsilon for which, Jason, 1 sec. So you give me an epsilon and I cannot give you a delta back, the limit doesn't exist. It's sufficient for 1 because it means it's not for any. So the limit exists only if you pick any epsilon on the planet, and for every epsilon you give me, I'll give you delta back. Any. Any means from negative infinity to positive infinity. Well, it has to be a positive number, but you know what I mean. Yes.
So, but if it was approaching from the left, it would have one, correct? If it was if you wanted the limit from the left or the right, there would be an answer.
Right, but
But not if you just wanted the limit.
correct. If you want to talk about from the right or from the left, but we are really talking about in general.
Okay.
Correct. Yes. Other questions? Let's look at an example, and then I'll give you the definition, and then we'll look at non-numerical. So we are on page. Why we do this is more because we want you to see this is basically the only proof we're going to look at, formal proof in this class. So at least this is, we consider that this is your first exposure to a proof, to a formal proof. And that's not going to happen again in this class. But it will happen in other classes. So let's take a look. It's on page 116, 117. I would like to start with problem 2. Let's start with a numerical example. Problem 2. Let me see how I am on time. I think I'm okay so far.
Are you going to write the definition?
Not yet. I want to look at the numerical example, and then I'm going to write the definition in plain English and symbols. Yes, both. But let's look at the numerical example first. Okay, use the given graph of f to find a number delta. So,
Sorry, what page are we on?
page 116, 117. So we're given a graph. I'm going to copy the graph. And here's the graph. And this, according to the graph, this is a 3. And this is a 2. And this is 2.5, and this is 1.5. And this goes 2.6 and 3.8. And they are telling us find the delta such that if 0 less than the absolute value of x minus 3, which is less than delta, then f of x minus 2 is less than 0.5. I will explain everything, what is every piece of information is telling us right now. Okay. So very clear from the graph, this is what I see in this graph. I see that this is a function f of x. It definitely has a limit. So I would say that the limit of f of x, when x approaches 3 from either side is definitely 2. There is no discussion there. If the function is defined at 3 or not, it doesn't matter. The limit from either side is 2. Agreed so far? Okay. So now delta is either this or this. We kind of have the answer once we understood from my previous example. We kind of understand what delta should be. Can anyone just give us an idea? What would you expect delta to be? This smaller. What is this distance? 0.4. What is this distance? So obviously, I will be choosing delta to be 0.4 in a minute. Okay, so that I know. Now, when I'm looking at this, what information do I get from what is happening on the y-axis? What does this mean? Exactly. So I know that epsilon is definitely 0.5 with no discussion. Would you agree? So this is the information I have from the graph already, that the limit is 2. The a value, which is here, right? A approaches 3 is 3, right? That
delta can only exist at 0.4 to be within.
Say it again.
So delta can only exist at 0.4.
So for this particular epsilon, which is 0.5, the corresponding delta must be 0.4. No questions about it. But now what I'm also interested is in analyzing what they are telling us here. Once we understand this, the definition that I'm going to write in a minute is going to be very clear. So without looking at this, we don't even know what it says yet, because I haven't explained, right? It's very clear from the previous example that we looked at. It's very clear that delta must be 0.4. For epsilon being 0.5, delta must be 0.4. If you say epsilon now is something else, then I will have to determine a different delta. So delta depends on epsilon. Yes?
Can you get why we're not looking at the other delta?
This is 0.4 and this is 0.8. If I use 0.8, then I could choose x here, which will fall outside of the interval around 2.
It would be outside.
Yes.
Yeah, it has to be within the delta.
Has to be
Delta
with
has to
it.
be-
F of x has to be within epsilon away from 2. Correct. Okay, so now we are trying to decipher what this is because this is part of the definition. So the problem is finished. We solved the problem. We were asked to find delta for this particular graph. We identified epsilon. We identified the limit. We identified a. We identified the limit, which is 2. and everything else is clear. But now what I'm interested in with this problem is clarify what this means. And let's discuss that. If I say to you the absolute value of 2, what am I really telling you? I'm telling you that this is the distance between
Positive and negative.
positive 2 and perfect. If I say the absolute value of x, what am I telling you?
Distance between x and 0.
Correct? But now stay with me, and I'm going to ask you, what is x minus 3 in absolute value?
Distance between x and 3.
Awesome. The absolute value of x minus 3 is nothing else but the distance between x and 3. So for now, we deciphered this piece. Why do you think there is a 0 less than the distance between x and 3, which is very clear? I mean, of course,
It'll be positive.
it is a positive. It's distance. So the absolute value of x minus 3 is always positive. But why do I have to write less than 0 less than this? What is the option that I'm excluding by saying
Equal to.
not equal to, in other words? But this is true also, right? I cannot pick x equals 3 ever. When x approaches 3, we talked that from
Yeah.
x cannot be 3. So this is what this says. It says you cannot pick x equals 3 because this will be equal to 0. And now, obviously, this says less than delta, which means exactly what I said a few minutes ago. I said, where can I pick x? I can pick x anywhere I want between 2.6 and 3, or 3 and 3.4.
Within delta.
But I cannot pick 3, right? Because this would be equal to 0. So then the distance between x and 3 is smaller than delta. I can pick anywhere between 2.6 and 3 and 3.3 and 3.4. But I cannot pick 3 because that would be equal to 0. So it's restricted. It cannot be 0. And I cannot pick 2.6 because it has to be strictly less than delta. So I can pick anywhere between 2.6 and 3, not 2.6 and not 3. And I can pick anywhere between 3 and 3.4, not 3 and not 3.4. This is what this says. Now stay with me. If I pick x here, what would happen to f of x? And can anyone decipher this for us exactly the way we deciphered that? What does that say? Epsilon. Exactly. Thank you. So this says that f of x minus 2. So when I pick x here, the distance between f of x, oops, sorry. So when I pick x here, the distance between f of x and 2 will definitely be less than 0.5, which is less than epsilon. So this is what this says. So let's write it. So this means the distance between f of x and 2 is less than epsilon, which in our example is 0.5. Now we have all the pieces to write the definition. And then we'll look at an example and move on. Okay, ready? Yes, please.
So is that the official definition?
No,
Oh,
I'm going to write it right now. Once I have these pieces cleared,
so sorry.
no, that's a very good question. I took away the excitement. So now we can write the full definition.
It was very suspenseful.
Yes, it was. So here it is. The precise definition of the limit, also known as, or the epsilon, what do you think? Delta definition of the limit. So they mean the same thing. We either say the precise definition of the limit, or we say the epsilon delta definition of the limit. Same thing. Ready? I'm going to write it in plain English first, and then in symbols. You do not have to use the symbols if you don't want to, but they will be very easy. Ready? Limit of f of x as x approaches a is L. What was a in my example?
3,
Or 2. Right. What was L in my example?
2.
Right, in the last one. Yes. So 3 was in the last example, and this was 2 in the previous example. This was 2, and this was 5. This is a double equivalency symbol. What does the double equivalency symbol say? It says this. From the left, I can show you the right, and also from the
Right.
I can show you the left. It goes both ways. Ready? For any or every, whatever you want to use, it's up to you. For any or every epsilon greater than 0, I will find a corresponding what? Delta positive, such that every time I pick, what do I pick?
X.
Yes, within x is at on the x-axis. Within delta from
X.
A.
from A, comma, f of x will definitely always, for every epsilon, will definitely fall within
Epsilon.
of
Delta.
L.
But cannot equal A.
Oh, we know that. When we say x approaches
I figure
A,
we might as well just keep adding them.
when x approaches A, we know x is not A. And why is that? Because
It approaches.
Oh, we are continuing.
that's it. Because what? The
Limit.
exactly. If it didn't exist, you could show for some epsilon and not for all.
Can you put X?
Yes. So let's look at it again. The limit is L implies that for any and every on the planet epsilon as small as you want, I will always find the corresponding delta, which will be around A, of course, such that every time I pick x within delta away from A, f of x, f of that, f of this x, f of this x, whatever I pick, will definitely fall within epsilon of L because the limit exists. So now here is, you have to write this definition when you get something like this. I don't recommend it. I do recommend a couple of mathematical symbols that you may say, I don't care for them, I'm not going to see them again. You may, however. So I hope you do. So here's what I like to write it. It's also in your text, and it's also on the checklist. Here it is. Limit as x approaches A from other side is L is equivalent to the following. And I'll explain every symbol, and it's very simple, I think. This is equivalent to exactly the same sentence we just used. For every epsilon greater than 0, there exists a delta greater than 0. I'll explain in a moment. Such that 0 less than the absolute value of x minus a is less than delta will imply the distance between f of x and L less than epsilon. And that's it, instead of the whole page.
That's it.
So
Piece
this
of
symbol is for any. So please write it down.
Okay.
Upside down A, uppercase A is for any. For any epsilon greater than 0, the reverse E is there exists. There exists. I will
what?
find. There exists.
The reverse E means it exists.
There exists. I will find. I will find. There exists. For every epsilon greater than 0, there exists a corresponding delta greater than 0, such that this lowercase e, also backwards, such that.
Wait, which one is such that?
Right here, such that.
Or
Right
such
here, such that. Every time I pick x, that's what it says. We already talked about this. This is not new, right? We discussed it 5 minutes ago. That's why I did, so we don't have to ask now. Every time I pick x, delta away from a, not a, and not at the end of the interval. The result would be what? That the distance between f of x and the limit would be less than epsilon. So you only have 3 symbols to remember. There is nothing else. This one that means for any. This one that means there exists. And this such that.
You just ran space, what happened with it? It's like equal, is that equal?
Oh, it's an arrow.
It's an arrow. It's an arrow. That means that the distance between the f of x that I pick and the limit is less than epsilon. So there are 3 symbols. That would 3 symbols, but these 3 symbols replace 5 lines or half a page, and I think it's worth it. It's up to you. So you either memorize the definition as is, or you use those 3 symbols. I'm fine either way. Okay. So I would like to look at an example. Let's say problem. I'm looking at the checklist because I don't want to do the same problem.